Hello everyone, welcome back to my channel. My name is Dr. Yogita Bish and this is the third video of video series called chemical bonding. In the earlier videos, we talked about the few approaches given by the Lewis-Kosel approach and which were further modified by the Langmuir, and there we understood the covalent and the electrovalent bond. And in the further videos we will talk about how to draw exactly the Lewis structure step by step. But before that we should know about certain terms. So in today's video I'm going to cover those terms here. So this will include the covalency calculation, how to identify the covalency of the atom, and the total valence electron calculation, how to check the bond pair electrons, lone pair electron, and also how to calculate the formal charges. All these topics are very important to exactly draw the structure of the Lewis structure of any molecule. Okay, so we'll begin with the covalency. So what is covalency actually? First we will try to understand the definition and I'll explain it with the help of the example. So covalency is basically equal to the number of unpaired electron in the orbital of the valence shell of an atom in the ground state or in the excited state. So there are so many things to focus on. So first of all, you should know what is an valence shell. Okay, so I'll explain it with the help of example. For example, let's say we talk about nitrogen. So it has 7 electron. Its configuration is 1s2, 2s2, 2p, 3. Total 7. Right? So here 1s2 is the inner shell electron, whereas the 2s2 and 2p3 are the valence shell electrons. So basically valence shell electron is here 1 and 2, these are the principal quantum number. So whatever the maximum principal quantum number is there, in that particular principal quantum number, how many electrons are there, that will signify the valence shell. So here the maximum principal quantum number is 2, right? So that is why we have 2s and 2p, and there the available electrons are 2 and 3, that is why we have total 5 valence shell electrons. So here we don't have the d shell. Why? Because in case of when n is 2, L is given by 0 and 1, so this is S, this is P, so D is not possible in this particular case. Okay, so if I draw this, so 1s is of no use in this case of in case of nitrogen. We will focus on 2s2 and 2p3. So if I have to draw this, I can draw it like this. This is also another way of representation, right? So this is how we can draw here. Okay, so this is 2s2, 2p3. So according to this definition, it is equal to the number of unpaired electron in the orbital of the valence shell. So this is the valence shell. How many unpaired electrons are there? 1, 2, 3. Okay, this is only in the ground state possible. Here the excitation is not possible. Why? Because we don't have the orbital, like we don't have 3D for the excitation of these electrons in the s orbital, right? So unpaired electrons are 3. Therefore, in case of nitrogen, covalency is 3. That is why you must have seen that NCl3 is possible, but NCl5 is not possible. Why? Because it has 3 unpaired electron. 5 is not possible in this case. Okay. Similarly, we can take example of oxygen. Okay. In case of oxygen, we have 8 electrons. So it is 1s2, 2s2, 2p4. Okay, so 1s2 is of no use for us, so we will focus on these two. So in this case we can show it like this, right? 2s2, 2p4. So how many unpaired electrons are there? 2, right? So its covalency is 2. Okay, so that is why OF2 is possible, but OF4 or maybe OF6 is not possible in case of oxygen. Okay, then let's just move to the some other element which belong to something which has also have the d orbital. Okay, for example phosphorus. Okay, so in case of phosphorus, we focus on the only the valence shell electron. Okay, so the valence shell electron configuration is 3s2 3p3, and it also have d orbital, though it is empty, but it also have d orbital, so 3d0. This is the configuration for phosphorus. Okay, so here if I draw this configuration, you will see this is 3s, this is 3p, okay, and of course 3d is empty. Okay, so this is in the ground state without excitation. Okay, so in this case you can see you just have to check the number of unpaired electrons. So 1 2 3, there are 3 unpaired electrons, therefore in the ground state its covalency is 3, right? So that is why let's say PCl3 is possible. Okay, now in case of first excitation, excitation means when you do the very first excitation whichever is available, so it is possible to excite this electron to the d orbital. So in that case what will happen, excitation state, the first excitation state where we are doing the first excitation, so in that case how many unpaired electron we will left with, you can just check. This is 3s 3p and one electron has moved to d orbital. Okay, so 1 2 3 4 5, right? So 5 unpaired electrons are possible here, so that is why PCl5 is possible. So in first excitation state its covalency will be 5. Okay, so that is why phosphorus shows covalency of 3 and 5. Okay, we'll take one more example and then we'll move to some other term. Let's say we talk about chlorine. Okay, so chlorine has a configuration of, it has total 17 electron. So let me just write down the complete configuration: 1s2 2s2 2p6 3s2 3p5, and of course 3d is empty. So in this case highest principal quantum number is 3. So these are my valence electron and these are my inner shell electrons. So we will not talk about this, we will focus on the outermost shell electron. So how can we represent it? 3s2 3p5. Okay, 1 2 3 4 and 5, and don't forget in case of 3 principal quantum number, when n is 3, possible L values are 0 1 and 2, that is why S P and D is also possible, though D is entirely empty, still it is there. Okay, so this is in the ground state. So in ground state you can easily see how many covalencies are possible. 1 is possible, right? Only one unpaired electron is there, so 1 is possible. Okay, so that is why for example HCl is possible, okay, where it has the covalency of 1. Okay, now you can easily see that there are many excitation possible. Okay, one possibility is that this can move to the, one electron from the 3p can move to the 3d orbital. Okay, so in that case this is called as excitation state first. In that case covalency you need to check. So first we will draw all the electrons once again. So 1 2, and here we will have, yeah, okay, so how many unpaired electrons are there? 1 2 3. So in the first excitation the unpaired electrons are 3, that is why the covalency which is possible is 3. Okay, and the one of the example is ClF3. Okay, so here it can form 3 bonds. All right, now there are other possibilities as well. So this electron can also move to the empty d orbital. So that will be considered as excitation second. Okay, and let's see how many covalency will be there in this case. So here 1, 2, 3, this has moved to the d orbital. So in d orbital we have 1, 2. So 1, 2, 3, 4, 5. 5 unpaired electrons are there. That is why 5 covalency is also possible. Example is ClF5. And then another possibility is also there. The electron from the 3s can also move to 3d. So that is also possible. So in that case, we will have 1, 2, 3, 4, and then 5, 6, 7. So in excitation state 3, covalency possible is 7. What does it mean? It means chlorine can show these many covalency. It can show 1, 3, 5 and 7. Okay. So these terms, this covalency, though you must have studied it earlier, but this is very important to remember, because while drawing the Lewis structure, we need to take into account the covalency of the central atom. So sometimes we end up making such structure where those covalency is not possible. Okay, such case of oxygen or maybe sulfur. Okay, so try to remember that. We'll take one other example. Phosphorus we are done. Then let's just quickly take sulfur, because sulfur is also one of the very commonly used central atom in case of Lewis structure. So in case of sulfur, we know the configuration is 3s2 3p4, and of course 3d is empty. Okay, so in this case the covalency would be 1, 2, 3 and 4. This is 3s2 and 3p4, and of course 3d is empty. Okay, so this is the covalency in ground state. So there is no point of guessing that in case of ground state how many unpaired electrons are there, only 2. So that is why in the ground state the covalency possible is 2 for sulfur. Okay, same as that of the oxygen. But wait, here in case of oxygen and sulfur there is one difference. In case of oxygen there was no d orbital. That is why this was no excitation possible. But in case of sulfur we do have the d orbital, right? So excitation is possible. Okay, so excitation state first. In that case the covalency would be, let us just check. So we will have 1, 2, 3 and 1 here. Okay, so 1, 2, 3, 4. So in that case, first excitation, the covalency of the sulfur would be 4. So in case of sulfur, it can make 2 bonds. It can make 4 bonds. Can it make more bonds? Let's just check. So yes, we do have the paired electron in the s orbital. It can move to the d orbital. So we can have the second excitation covalency as well. Okay, so that will be 1 electron here, 1 electron in 3p, 3 electron in 3p and 2 electron in 3d. So this will be 1, 2. So 1, 2, 3, 4, 5, 6. So sulfur has the tendency to show covalency of 2, 4 and 6. It cannot show the covalency of 5. Okay, so please do remember these things, these covalency term, while we will look for the covalency of the central atom while we draw the Lewis structure. Okay, so that was about the valence electron. Okay, now let's just move some other terms that you should remember. These are called as total valence electron, total bond pair electron, total lone pair electron and the formal charges. Okay, so the second term that we are going to discuss today is total valence electron. Okay, So valence electron, you already have the idea, like in case of chlorine I explained to you, right? So the valence electron are the one which has the electron which are present in the highest principal quantum number. In case of chlorine, 1s2, 2s2, 2p6, these are the inner shell electron, but the valence electrons were the 3s2 and 3p5. So that is why the total number of the valence electron in case of chlorine is 2 plus 5, 7. Okay, so the one which are present in the outermost shell. So in case of molecule, what will happen? Total number of valence electron basically represent the total number of valence electron of all the atoms present there. Okay, I'll give you an example of let's say water. Okay, so in this case, the valence electron of hydrogen, it is the sum total of all the valence electron of atoms present in a molecule. Okay, so in case of hydrogen, valence electron is 1s1, that is 1. In case of oxygen, it is 1s2, 2s2, 2p4. So valence electrons are 6. We don't take into account the innermost shell, right? Only the outermost shell. So in case of oxygen, the valence electrons are 6. In case of hydrogen, the valence electron is 1. So total valence electron for water, it will be 2 into 1. 2 means 2 hydrogen, 1 means for each hydrogen 1 electron is there, plus 6 for oxygen, that is total 8. Okay. What about the third term, bond pair electron? Bond pair electron means how many number of bonds are there multiplied by 2. Number of single bonds multiplied by 2. Okay, if again I take the example of water, so if I draw something like this, please don't go by the shape, as Lewis structure never talk about the shape, it only talk about the structure. So okay, so water actually has a band structure, but here we are just talking about the Lewis structure, so that is why I'm just drawing it basis on the not on the basis of the shape, just totally based on the number of atoms present there. Okay, so oxygen is bonded to 2 hydrogens. So how many bonds are there? 1, 2. So number of bond electrons would be 1, 2 multiplied by 2. 2 single bonds are there multiplied by 2. So total bond electrons are 4. Okay, and then finally we have number of lone pair electrons. Okay, this was bond pair electron. Bond pair electrons. Okay, so number of lone pair electrons, this is given by total valence electron minus number of bond pair electrons. Okay, so in case of water, we have already seen the total number of the valence electrons were 8 for water. It will be 8 minus number of bond pair electron were 4. So that is why number of lone pair electron would be 4. Therefore, water has 4 lone pair of electron. Okay, but this is not the strict rule. Reason being, this is just a formula for the lone pair, but sometime we use this lone pair to form double or triple bond. Okay, to satisfy certain condition. To satisfy certain condition. Okay, so please do remember, this formula will give you the idea about the lone pair, but this lone pair will not remain as a lone pair. Most of the time it will remain, but sometime we have to convert this lone pair into double bond or maybe sometime triple bond. Okay, I'll give you another example of let's say ammonium. Okay, it has NH4 positive. So please tell me how many total number of valence electrons are there in this molecule. So nitrogen, the valence electron for nitrogen is 5, plus for hydrogen is 1 into 4. Okay, but here we also have a charge. Okay, so whenever we have charge, what to do in that case? When we have positive charge, subtract it when we have negative charge, add it to total valence electron. Okay, so in this case this is plus, that is why I have to subtract it, minus 1. So it will be 8. Okay, so total valence electron in case of ammonium ion is 8. Okay, what about the bond pair electron? So nitrogen, hydrogen, 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 hydrogen. How many bonds are there? 4, right? So number of bonds pair electron will be 4 multiplied by 2, that is 8. Okay, and what about the lone pair electron? Lone pair electron is total number of the valence electron, total number of valence electron minus bond pair electrons. So that is 8 minus 8, 0. So there are no lone pair electrons are there in the ammonium. Okay, I'm not going through the charges and all those things. I'll take that in the next video. I'm just giving you the idea like how to calculate the lone pair electrons, bond pair electron. And I've already told you lone pair electron will not remain as it is. Sometimes we use it for the double bond or maybe sometime for the triple bond. Okay, let's just take one last example, then we will move to the formal charges. That is CO3 2 negative. Okay, carbonate ion. Okay, so total number of valence electron in that case would be, for carbon we have the total number of valence electron is 4, plus for oxygen it is 6 multiplied by 3, and we have negative charge. So I have already told you, whenever we have the negative charge we have to add it to the total charge. Okay, so we have to add plus 2. Okay, so total we have 24. Okay, bond pair electron, how many bond pair electron would be there? Carbon, oxygen, oxygen, oxygen. Okay, I'm not drawing the exact structure, I'm just showing you the single bonds. Okay, so bond pair electrons is whatever single bonds are there, 1 2 3 multiplied by 2, that is 6, right? So how many lone pairs are there? Lone pair electrons would be 24 minus 6, that is 18. So this is lone pair electron, or will be used for double bond or triple bond. Okay. So this was about the bond pair lone pair electron calculation, and the last topic that I'm going to cover in this video is quickly the formal charge. Okay, and if you don't understand this in detail, don't worry, I'm going to explain this in the next video with the application. Okay, so we have the next topic called as formal charge. Okay, so I'll give you an example. Okay, so you must have seen resonance structure. That means a single molecule can exist in two or more than two form, right? And all are possible, but one form will be more stable. It will have lesser energy as compared to the other one. Okay, so these structures are called as resonance structure. Okay, so in this structure you will see that they have certain kind of charges on each atom. For example, I'll give you example of carbon dioxide. Okay, so in case of carbon dioxide, the possibility is this one. Okay, it can have this charge, or it can also have, let me just draw the lone pairs also. Okay, or it is also possible to have this structure. 1 2 3 4 5 6 negative. Okay, both structures are possible. So here you can see some positive negative charge over here, and there is no charge. So sometime normally when there is no charge we don't show anything, but right now I'm just showing with 0. Here this oxygen, this carbon, this oxygen, they don't have any charge, they have 0 charge. Okay, so how to calculate this charge? This charge which is there on individual atom is called as formal charge. Okay, and there is a formula for that, so we are going to do that and learn that. And then there are certain rule also on the basis of which you can predict the stability, like out of two structure, on the basis of the formal charge, which one is more stable as compared to the other one. Okay, so the rule for this is formal charge. Okay, formal charge, the formula here is valence electron minus lone pair electron minus bond pair electron divided by 2. Okay, this divide by 2 is only for the bond pair electron. Okay, so let's say we do this for A. Okay, this is A, this is B. Okay, and if I have to calculate the charge on these atom, individual atom, I'm giving this term 1, maybe this is 2, this is 3. Okay, and this is again 1 2 and this is 3. Okay, so first in case of A structure, that is this one. Okay, this is first, this is second, this is third. Okay, so first I'm calculating the formal charge on the first structure. Okay, this oxygen. Okay, so the formula is valence electron. So we know that for oxygen the valence electron is 6 minus lone pair electron. So how many lone pairs are there? 1 2 3 4 minus 4 minus bond pair electron. How many bond pair electrons are there? 1 2 3 4. For each single bond we have to count it twice. So for this 2, for another bond 2, so total 4, right? 4, and there is another divide by 2 also, divide by 2. So how many charges are there? 0. So that means there is 0 charge on this. And you can see first and second are similar, so this will also have 0 charge, right? Then what about the formal charge on third carbon? So we know that the valence electron for carbon is 4 minus, how about the lone pair electrons? So there are no lone pairs, so minus 0 minus how many bonds are there? 1 2 3 4. 4 2s are 8, right? So because for each single bond I have to count twice, right? So 8 bond pair electron divide by 2. So again this also have a 0 charge, right? I hope this is clear. Now let's just move to the structure B. Oxygen, carbon, triple bond. Okay, 1 2 3 4 5 6 and 1 2 this. Okay, and this is considered as 1, let's say. This is 2 and this is third. Okay, so let's just calculate the formal charge for first is oxygen. Again, the total number of valence electrons are 6 minus lone pair electrons are 1 2 3 4 5 6 minus bond pair are 1 means 1 into 2, 2 divided by 2. So its charge is minus 1. That is why this has minus 1 charge. Okay, what about the second oxygen? The formal charge on second. Okay, so for this we have how many? 6 valence electron. The lone pair electrons are 2 minus the bond pair electron are 1 2 3 3 2s are 6 divided by 2, right? So this is plus 1. So it has plus 1 charge. Okay, what about the carbon? The formal charge on the carbon, that is the third one. The total valence electron for carbon is 4 minus, there is no lone pair electron, minus 1 2 3 4, 4 2s are 8 bond divided by 2, that is 0. So the formal charge on carbon is 0. Okay, so I hope this is clear how to calculate the formal charge on each and every atom. Okay, now I told you, like, on the basis of the formal charge we can literally guess the stability, like which structure, like both are possible, right? Because both are satisfying all the condition of like octet, it should complete the octet and all those things. I'll talk about those rules later on. But both structures, the first A and the B, both seems to be completing all the rules. Still one is stable than as compared to the other one, and there are certain rule for that, how to decide, like on the basis of the formal charge. And formal charge is one of the major deciding factor to discuss the stability of a particular molecule. Okay, so there are certain rules that I am writing, you need to remember that, so that just on the basis of the formal charge you can guess the stability of a structure. Okay, so rules for best formal charge. First rule is fewer formal charge. What does it mean? It means in any molecule, if any of this atom has a fewer charge, that means it is going to have a better stability as compared to the an arrangement where there is a possibility of the charges. So this is better stability, and stability is inversely proportional to the energy, so that means it has a lower energy. Secondly, lower magnitude. What does it mean? It means if some, in particular case, if plus 2 is there on one of the atom and in other plus 1 is there, then plus 1 would be preferred as compared to the plus 2. Okay, this is the meaning of this particular second rule. Third, negative charge on more electronegative atom. Okay, so if you come across any situation where the formal charge are exactly the same, even the magnitude is same, then you have to look for like on which particular atom it is there. If it is there on the more electronegative atom, the negative charge on more electronegative atom, that means it is more stable. Okay, so on the basis of these three we can easily judge which one is more stable as compared to the other one. Okay, if I compare with A with B, So it is quite clear from the very first rule itself that fewer formal charges means better stability. So in case of A, we don't have any charge at all. Whereas in case of B, though overall charge is 0 because plus 1 minus 1 will cancel out, but still on individual atom we do have charge. Okay, so there is no point of guessing that A is much more stable as compared to B. Though B also possible, it may be present in some percentage, but A most of the time it will present in terms of A. Okay. Similarly, I'll take another example. Sulfate ion. Let's just draw the sulfate ion. How to draw that, I'll explain that in the next class. Okay, right now I'm just showing the structure along with the charges. Okay, let's say sulfate ion. Okay, it has 2 negative, total charge 2 negative. So we can draw it like this: oxygen, 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 with 1 2 3 4 5 6, 1 2 3 4 5 6. On each and every oxygen I have 6 lone pair electrons. Okay, and on each we have negative charge. I'm not going to show the calculation for each and every atom. You can do it, or we will talk about these atoms again in the next video, so you can just check there. Okay, I'm just giving you the idea like how to apply these rules. Okay, this is structure 1. Then the another possibility with sulfate is that it can form a double bond here. Okay, and then in that case there will be double bond here, single bond with other oxygen, and 1 2 3 4 5 6 minus 1, 1 2 3 4 5 6 minus 1, 1 2 3 4 5 6 minus 1, and this sulfur has plus 1 charge. Okay, here sulfur has plus 2 charge. This is B. Lastly, we have the another possibility that it is making double bond with 2 different oxygen and single bond with rest of the 2 oxygen. 1 2 3 4, 1 2 3 4. Here we have 0 charge, and 1 2 3 4 5 6 minus 1 2 3 4 5 6 minus. Here this sulfur doesn't have any charge. Okay, this is called as C. Okay, so if I compare A, B, C, you have to tell me on the basis of these rule which one is more stable as compared to the other one. Okay, so as per the first rule, the fewer formal charge, so the one which has the least number of charges. So here each and every atom has a charge, here also, but here only 2 atoms have the charge. Okay, so of course C is the most stable one. Okay, this is the most stable one. What about these two? Now we look for the lower magnitude. So here each and every has a charge, but in this case this doesn't have charge. Also here the magnitude of the charge on sulfur is plus 2, whereas here it is plus 1. So of course if I compare A with B, B seems to be more stable as compared to A. Okay, similarly you can also get some example where we have the negative charge on more electronegative atom. If you come across that, that means that will be more stable as compared to the rest of the structure. Okay, so that was about the formal charge. I hope you got some idea about the formal charges, the covalency, and how to calculate the total valence electron, bond pair electron, lone pair electron. So we are going to use all this information to draw step by step the Lewis structure in the next class. Okay, so I'll see you in the next class. Thank you.